The next topic is conduction and resistance. This is chapter 3.1 part 5. Previously we saw resistivity, and before that we saw the Ohm's law equation and the IV characteristics or IV graphs of different components, including ohmic and non-ohmic conductors. So by the end of this section you should be able to explain conduction in metals, explain electrical resistance, calculate the drift velocity of conduction electrons in metals. We also saw why the resistance of a metal increases with increasing temperature. So we will see some more details here as well. How the metals conduct also I explained earlier. Explain electrical resistance, calculate the drift velocity. Now this is something new. We have something called the transport equation here, and in that transport equation we will see a V. That V is the drift velocity. Briefly we will go through. Here you can see, now this is a metal or a conductor. You can think that this is a wire. Wire is cylindrical in shape. Then here you can see those are the metal ions, the plus are the metal ions. Then we have the transport equation, that is this: I equals nAvq. I equals nAvE is for a metal. Now in a metal the conduction occurs by the electrons. In other words, the charge carriers are the electrons. But in something else, maybe in a solution, when you learned about electrolysis, there the charge carriers are ions. So the ions at electrons. Now even a beta particle or a alpha particle is a helium nucleus. So that when it is moving, there is a current. Any charge that is moving means there is a current. You can even have a proton moving. That is also a current. A hydrogen nucleus or a proton moving is also a current. So depending on the situation, we can use the equation I equals nAvq. But almost always, because we are dealing with wires, the conduction or the charge carriers are the electrons. That's why we have this equation I as I equals nAvq, nAvE, where E is the charge on an electron. Now if we have I equals nAvq, Q is the charge on a charge carrier. And we saw resistivity previously. You can see here, by the way, there is something more in this equation, that is N. N is called the number density. In other words, that is the number of charge carriers per cubic meter. In a wire, the charge carriers are electrons, so that is the number of conduction electrons in a cubic meter. This is a very important equation. It's called the transport equation. I equals nAvq. I can actually draw a diagram and explain all this. Then here you can see, and by the way, this V in this equation is the drift velocity. A is the area of cross section of the conductor. And different materials have different values of N. N is the number density or the number of charge carriers per cubic meter. All of this you can see, these two are metals, these are semiconductors, but in all of them the charge carriers are electrons. So the number of charge carriers or number of conduction electrons per cubic meter is this. And then we have finally in each part we have the definitions. Normally in the last page of that part of the chapter, the slow overall movement of the charges in a current is called the drift velocity. Now these are definitions, so you have to memorize them with understanding, because in the exam paper they can ask you define drift velocity. Then this is what you need to write. So make sure you memorize these definitions with understanding. The transport equation is I equals nAvq. This defines electric current. I from a fundamental basis. It is the product of charge carriers, N the charge of those charge carriers, Q the cross-sectional area of the conductor, A and the drift velocity of the charge carriers in that conductor, V. So all the terms are, all the quantities are defined here. I is the current, it is the product, so I equals Q over T. and it is the product of, now I is the product of these, and what is N? Product of charge carriers N, the charge on those charge carriers Q, the cross-sectional area of the conductor A, and the drift velocity of the charge carriers in the conductor V. So N is the number of charge carriers per cubic meter. We will see the details. And here you can see drift velocity is the slow overall movement of the charges in a current. Slow overall movement of the charges in a current. Alright, so I spent some time there because it is important. Now we will go back. Explain conduction in metal. So how does the conduction occur? So when I was discussing the Ohm's law chapter, the IV relationships, current voltage relationships, that is chapter 3.1 part 3, I explained this, but we will see. In order to conduct electricity, solids need to have electrons that are delocalized from the solid's atoms. Remember the delocalized electrons? Wait, I will go back to that, then it's easier. So you have the metal ions here, and then each metal atom gives the electrons that makes those metal ions. So when the atom gives an electron, it becomes a positively charged metal ion. That's why we have the circles with the pluses here. The circles with the minuses are the electrons that those metal atoms gave to the sea of electrons. We have the conduction electrons in the sea of electrons, and that is also what is shown here. You can see here the orange circles with the pluses in them are the metal ions, and the black circles are the electrons that those metal ions gave to the sea of electrons. These electrons are called delocalized electrons. They are also called conduction electrons or the charge carriers. In order to conduct electricity, solids need to have electrons that are delocalized from the solid's atoms so that they can move through the solid, causing an overall movement of charge, a current. So current is the rate of flow of charge. Conduction in metals. The structure of metals has a regular lattice of metal atoms. You would have learnt about this when you learned the metallic bond for chemistry. So here we will see something about it again. So the structure of metals has a regular lattice of metal atoms. These are bonded together through the sharing of electrons, which act as if they were associated with more than one atom. Many of the atoms also have an outer electron that is not needed for bonding between the atoms. So for example, I mentioned earlier, if you take sodium, which is in the first group of the periodic table, which means it has one electron in its outermost shell. Now this electron is given to the sea of electrons. So then sodium will become Na+, which is the sodium ion. You can say that it's shown by this circle here. This is sodium. Now if it was magnesium, magnesium is in group 2, so it has 2 electrons in the outermost shell. These 2 are given to the sea of electrons. Then that will make that magnesium atom Mg2+ ion, magnesium 2+ ion. If it's aluminium, aluminium is in the 3rd group of the periodic table, so it will give 3 electrons per atom to the sea of electrons, which means it will become aluminium 3+. So by the way, these are the delocalized electrons, conduction electrons, or free electrons. Yeah, that's the word I was waiting for, the free electrons. So you have 3 names for them: conduction electrons, free electrons, and delocalized electrons. Make sure you remember them because you might see one word or the other word. These are bonded together through the sharing, that is the metals, metal atoms. These are bonded together through the sharing of electrons, which act as if they were associated with more than one atom. Many of the atoms also have an outer electron that is not needed for bonding between the atoms. These free electrons have a random motion which changes as they collide with atoms of other electrons, but on average, the overall position of all the charge in the metal is stationary. So that is if there is no current applied to it. But once a potential difference, not current, once that is without a potential difference applied to it. But once a potential difference is applied, those electrons will move towards the positive terminal of the power supply, because electrons are negatively charged, so they will be attracted to the positive terminal. Now on this side, this is the negative terminal, negative repel. So overall, these electrons, the delocalized electrons or the free electrons, or also called the conduction electrons, will move to the right. They will move in the clockwise direction. So when there was no EMF, or rather potential difference applied across this, then they were randomly moving. So overall, there was no movement. That's what they said here. These free electrons have a random motion which changes as they collide. Collide with atoms or other electrons, but on average the overall position of all the charge in the metal is stationary. However, if a source of EMF is connected across the metal, the electric field is set up in the metal will have a tendency to push the negative electrons towards the positive end of the field. Now if you think of this as an electric field, here you have a positive because there is a positive terminal, here you have a negative. So remember, the electric field is always from the positive plate or positive terminal towards the negative terminal or negative plate, because the electric field lines always is pointing away from the positive and towards the negative, and the electron will move in the direction opposite to the electric field, because the electric field is showing the direction of the force on a positive charge. So the positive charges, the force on them will be to the left due to the electric field, but on the electrons it will be to the right. Now the positive charges are the protons. They are effectively locked in the nucleus, so they cannot move, but the electrons, they are free electrons. That's why the electrons move and not the protons. However, so I went through this, sets up the metal will have a tendency to push the negative electrons towards the positive end of the field. The slow overall movement of the electrons is called their drift velocity. Now you have a drift velocity when there is a potential difference applied across the metal like this. See, okay, it's shown here. You can see the direction of the electric field, like I said, is to the left, because it is always pointing away from the positive plate or positive to the negative, like this. Electric field from EMF is to the left. The purple lines indicate that. Then a net displacement in the direction of the positive side of the EMF is superimposed on the random thermal motion. So the electrons are moving. Now see, this is the electron, it's moving here, but it is attracted to the positive side. So it doesn't go in a straight line like this, because there are other electrons and there are also metal ions. So even if it tries to go like in a straight line, what will happen? There would be another electron here, it will collide with that. So instead it will go that way, it will collide with this that way, and eventually it will move to the right. So this slow overall movement of the electrons is called their drift velocity. A net displacement in the direction of the positive side of the EMF is superimposed on the random thermal motion. Conduction in metals happens as the free electrons add an overall movement along the direction of the voltage across the conductor towards the positive anode to the random collisions and vibrations. Okay, so I think this sentence is clear now. The positive terminal is the anode because it attracts the negative charges. Remember, for electrolysis chemistry you would have learned the cathode and the anode. Anode attracts the anions, so it has to be positively charged. Cathode attracts the cations, so it has to be negatively charged. Cations are the positive ions, anions are the negatively charged ions. So because of this, the electron moves that way and therefore you get a current. That is what is explained here. Conduction in metals happens as the free electrons add an overall movement along the direction of the voltage across the conductor towards the positive anode to their random and random collisions and vibrations. So there will be random collisions here, these ions are vibrating, but what will happen? Eventually it will move that way because of that potential difference or the EMF that was applied, which causes them to go that way. So because they have a net displacement or net movement that way, there is a current. Then you can see the transport equation. Now over here what is important is this equation, and here you can see the derivation of the equation. Again, that is also simple. Did you know, for a metal, the random thermal motion of the free electrons will be at speeds of thousands of kilometers per second. So that is the random thermal motion of the free electrons. Now, when you learned about temperature, I think in the 91 and O-level classes, you would have learned about temperature. Temperature is a measure of the average kinetic energy of the particles. So the greater they are vibrating or the faster they are moving, the greater is the kinetic energy, so the greater will be the temperature. Now anything, if you consider any object, all the objects are above 0 Kelvin, because at 0 Kelvin they will not be moving, we can say, but everything is above 0 Kelvin. So because of that, all those atoms, those particles will be moving, they will be vibrating if it's a solid. That's why they are always moving, so they have kinetic energy. Now the electrons will also therefore be moving, so the random thermal motion of the free electrons, because they are above 0 Kelvin, free electrons will be at speed, the speeds there will be at speeds of thousands of kilometers per second, whereas the drift velocity, now you learned what is drift velocity. You get the drift velocity when you apply a potential difference across the conductor. So as a result, the overall movement of the electrons to one side, to the positive, towards the positive terminal, will result in the drift velocity. Now this drift velocity during conduction obviously happens, is usually only millimeters per second. That is the comparison. Now when there was no potential difference applied across the conductor, the electrons were moving randomly, and that is what we call random thermal motion, and that was at speeds of thousands of kilometers per second. But once you apply the potential difference across the metal, now you have drift velocity, but that is only a few millimeters per second. Later there is a calculation, you can see here, we calculate the drift velocity here, it is 0.97 millimeters per second. It's very small, so it is only a few millimeters per second. Now based on this, you can understand, when you do a calculation like this, if you get a value, maybe a very high value, that means there is something wrong. So make sure your answer is sensible when you finally get the answer. The value of the electric current in a metal can be calculated from the fundamental movement of electrons. If we remember the definition, remember I equals Q over T. Current is the rate of flow of charge. If we consider the cylinder shaded on the diagram in figure B, so figure B is this one, a section of a metal wire with dimensions to show how to make calculations using the transport equation. If we consider a cylinder shaded on the diagram in figure B as the length of the wire that the charges move through in a time delta t, see, they move from there to there, then we need to calculate how much charge flows through it in that time. There are n electrons per cubic meter of this metal, and the wire has a cross-sectional area A. So n electrons per cubic meter of the metal, and the wire has a cross-sectional area A. So let's say the area, yeah, here you can see it's labeled, this is the cross-sectional area, that is A. Then and there are n electrons per cubic meter. Their movement is at a drift velocity v, and the distance this takes them along the wire in that time is delta x. So remember, displacement is equal to velocity times time, or we can say velocity is displacement divided by time. That is this equation. The total charge will be the number of electrons multiplied by the charge on each. The charge on an electron, we can call it E. So n times E will give you the total charge. I think that's clear. Now you have n number of charge carriers or electrons, and that times the charge on a charge carrier is n, will give you the total charge. The number of electrons will be their density. So number of electrons in a cubic meter, that is called the number density, n, simple n, what you have here in the equation. The number of electrons multiplied, the number of electrons will be their density, n, multiplied by the volume of the cylinder V they travel through in delta t, in the time period delta t. So you have seen the equation, the Q, the total charge will be n times, now n times E will give you the charge, and then in that specific volume. So the volume here you can see, now if you take this volume here, capital V is used for volume, simple V is used for the drift velocity. If you look at the volume of this, so that is the area of cross section here times delta x. The volume of a cylinder is area of cross section times the length. So capital A times delta x will give you V. So capital A times V, you see V is what? Capital A times delta x, but delta x is what? V times delta t. Can you see that here? V times delta t is delta x. So it's A times delta x. See, A times delta x, that is equal to V. Over here you can see that V is A times delta x, but delta x is V times delta t. So that's why instead of writing delta x, we have written V times delta t here. So you have n times V times E. So n times A times delta x, so that is V, then times E. Now delta x is V times delta t. See, it's already shown here. So n times A times V times delta E times E is what we have here. Now I is delta Q over delta T, definition of current. Then delta Q, you can write this whole thing here, n times, you can see n here, E here. So you have this. So we write what is here for delta Q, because delta Q is equal to that. Then divided by delta T. Now what happens here? Delta T and delta T cancels. So this is for from here to here for that time delta T. The sea of electrons has moved forward a distance delta x, which is equal to V times delta T. The shaded volume is V. The shaded volume V is A times delta x. So that is clear. Now if you look at another book, this same thing is explained in a little bit of a different way, but you can stick to this method because this is what is explained to you in this book. And finally you get the transport equation. So what happened here? There are n electrons per cubic meter of the wire. Then this is wire at time t. A cross section of the wire is this. Cross section is cross sectional area is capital A. Then delta x. The sea of electrons is moving to the right with drift speed v. The sea of electrons has moved forward a distance delta x, and remember the displacement is velocity times time, so you can think of it that way. Then delta x is v times delta t, and the shaded volume is V equals A delta x. Volume is the area of cross section times the height or the length of the cylinder, that is delta x, so A times delta x. So we have this equation I equals nAvq. This is called the transport equation. Now let's do an example with this. It's this that you need to basically remember for these calculations mostly, but also you have to understand the derivation, because they wouldn't ask you to show the derivation in the exam, but you have to know it because they may test you something about maybe just a part of it. The transport equation example: how fast would be the drift velocity of the electrons in a copper wire which has a diameter of 0.22 millimeters and carries a current of 0.50 amperes? The number density of the conduction electrons in copper is 8.5 into 10 to the power 28 per cubic meter. Now you can see number density is number of electrons per cubic meter. So number of electrons doesn't have a unit, but number of electrons per cubic meter. That's why we have the unit per cubic meter. So N has the unit per cubic meter, that is the SI unit. A has the SI unit square meters. V has the SI unit meters per second. E has the SI unit coulombs. I obviously has the SI unit ampere. The diameter is given. We need to find the area of cross section. A wire is cylindrical in shape, so the cross sectional area will be the cross sectional area of the wire, and the cross sectional area is area of a circle, that is pi r squared. Now pi times r is the diameter divided by 2, so 0.22 divided by 2, that is 0.11, and milli is 10 to the power minus 3. So if you write it in scientific notation or standard form, it will be this, because we have to place the decimal point after the first non-zero digit when we are writing in scientific notation. So you can see here wire radius, they write it in standard form, also called scientific notation. Even if you write it as 0.11 into 10 to the power minus 3 meters and do it, that's also fine. Then you have the cross sectional area here in square meters, SI units. Now you have A, you have what we are supposed to find here is V. So let's make V the subject of the equation. So V equals, well, when you cross multiply, I over nAe. Now I, you know, it's given. You can write, if you want, you can write the quantities that are given on a side. So then it's easy for you to figure out what is given and what you need to find. For example, something like this, by doing something like this. So I is given, N is this, that is also given. A you found. E is the charge on a charge carrier. In a wire, the charge carriers are electrons, so that will be the charge on an electron. We don't need to write the minus sign because we need the magnitude of the charge. We need the magnitude of the velocity, which is the speed. Now simple, substitute. I is 0.50, N is the number density. You can see it's here in SI units. Then A is the area of cross section that we found here again in SI units. Finally, E is the elementary charge, which is 1.6 into 10 to the power minus 19 coulombs. Everything here is in SI units, so your answer, you can see, will also be therefore in SI units. Now, to see what is this in millimeters per second, we can convert it to millimeters per second, because remember earlier we said that the drift velocity is only is only millimeters per second. So let's check that over here. You can see it's around that value, 0.97. If you convert this to millimeters per second, you get this, and they have rounded it off to two significant figures. Okay, so now you learned that equation, and also you learned how to do a calculation with that equation. Now we can maybe sketch some diagram for it. So imagine you have a cylindrical wire. Let me just change. Obviously, if they say why it's cylindrical, you have to assume it's cylindrical, because we don't have wires that are other shapes. Okay, so here I will use another color. Okay, so let's say A is the area of cross section of this, and then N is the number density. That depends on the material the wire is made of. Copper has one number density, iron has another, aluminium has another. It depends on that. Now what is the equation? I equals nAvq. But for a wire, the q is the charge on a charge carrier. For a wire, it is the charge carriers are electrons. So we can, instead of writing q, the charge on a charge carrier, we can write E. So for a wire, we get I equals nAvE. Now we will also write what these quantities are here. I is the current, A is the area of cross section of the wire. I have also labeled it there. Area of cross section. Of the wire, of the conductor. Now in this case the conductor is cylindrical in shape. Okay, so therefore this will be then pi r squared, because it's a circular cross section. Now, and also if they give you the diameter, you can write diameter divided by 2 squared over here. Then v is the drift velocity. DRIFT, drift velocity. And q is the charge on a charge carrier. Charge on a charge on a charge carrier. And in the case of metal, the charge carriers are electrons, so this will be the elementary charge, which is 1.6 into 10 to the power minus 19 coulombs. We don't worry about the sign, negative or positive. We write this because we need the magnitude, like I mentioned earlier. Okay, so this is what you need to know, the transport equation. I equals nAvE or nAvq. Now for unit 3, there are some experiments that you need to write about, or we can also say there are some practicals based on what you have learned. You should be able to apply that knowledge for the experiment or practical. So this is something like that you see here in almost every chapter, subchapter, you have something like this. So we'll go through that now. Investigating conduction velocity of colored ions. In this experiment, you will observe the movement of colored ions as charge carrier particles on a piece of filter paper soaked in ammonium hydroxide solution. A crystal of copper sulfate and one of potassium manganate will each dissolve. Okay, by the way, this is the Roman numeral 7. This indicates the oxidation number of manganese here. So potassium manganate 7. It was also called potassium permanganate in the past. Now to avoid the confusion, they wrote it like this and they call it potassium manganate 7, because if you say permanganate, somebody might wonder what does that mean. So it has been becoming easy and easy. Now in the past, for copper 1 oxide, copper 2 oxide, they used to call cuprous oxide, like that. So it was very confusing. Now gold, they have Au, aurium. Now again, so to make it easier and to avoid the confusion, this is used. Now if you look at, I will show you that I have shown the way to get this number. Now for chemistry, you would have learned this. So potassium, it is in group 1, so we have K plus. That will be the charge on this. Then if you separate it, because there is because of the bonding, the the ionic bond, so K plus and MnO4 minus. So between these two, it is a ionic bond. Again, these details you would have learned for chemistry, but inside this, you it is a different situation. Now we'll focus on the lesson now quickly. I want to just show you this. Now remember, this is MnO4 minus, so the overall charge on this is -1, so that's why I write -1. This is how you find the oxidation number of manganese. So let's call it X, we want to find it. Then the charge on this, the oxidation number of this plus the oxidation number of 4 of these oxygen ions should be equal to -1. That's what I wrote here. Now oxygen, it is in group 6, so 8 minus 6 is 2. That's why the charge on that is -2. For chemistry, again, you could have learned this. Now there are 4 oxygen atoms, so it's 4 times that, then it will be -8. So when you move it to that side, it will be 8 minus 1, which is 7. So this is the X is the oxidation number of manganese, and that is +7. That's how you get the 7 here. A crystal of copper sulfate and one of potassium manganate 7 will each dissolve, producing positive blue copper ions and negative purple ions of manganate 7. Connecting a potential difference of 30 volts across the wet filter paper will cause the ions to flow slowly across it in opposite directions, and their velocities can be measured using a ruler and stop clock. Expect a velocity of about 1 millimeter per minute. So you can see, observing the slow speed of ion movement during current flow. Here 0 volts, here plus 30 volts, microscopic slide, crystal, filter paper. So you will see it now. For biology, you would have learnt about photosynthesis. So there also you have something like this. Okay, so now I think it's easy for you to understand this. So this is actually to show that drift velocity in electrons. So that is analogous to this, we can say. Using this example is to help you understand the drift velocity. So basically it's very simple. What is happening here is, you have this filter paper soaked in ammonium hydroxide solution. Okay, so that is the first thing. Now this is used to, now what will happen is, the copper sulfate, a crystal of copper sulfate and one of potassium manganate 7, so both of them are placed here. You can think it's placed in the middle here. And why this is soaked? Because that will dissolve these ions. So you have a solid crystal, a crystal of copper sulfate and another crystal of potassium permanganate. You would have seen that in the lab. It is purple in color. Then copper sulfate, also you can see you have anhydrous and anhydrated. The hydrated one is blue, anhydrous one is white. So you place each of them here. Okay, then what happens is, a crystal of copper sulfate and one of potassium manganate will each dissolve, producing positive copper blue ions, that is from the copper sulfate you get the copper ions, and negative purple ions of manganate 7, that is from the potassium manganate 7. So what will happen? One is positively charged, that is you have the copper ions, and the manganate ion, which is this one, MnO4 minus, that is negatively charged. Now because both are colored, you can see them moving. One is purple, the other is blue. Then the copper sulfate ions, the copper sulfate. So what will happen is, the negative ion will move towards this positive plus 30 volt end, and the other one will move towards the less positive or the negative end. It will move towards this side. So connecting a potential difference of 30 volts across the wet filter paper. Remember, this is an ammonium hydroxide solution, which means it is wet, it is dissolved in water. That's why you have a solution, otherwise you can't get a solution. For chemistry they have learned this. will cause the ions to flow across it in opposite directions, and their velocity can be measured using a ruler and a stop clock or stopwatch. See, the ruler can be used to measure the distance and the stopwatch can be used to measure the time. This way you can get the velocity, and it will be about 1 millimeter per minute. So very simple experiment, and that is to observe the slow speed of ion movement through during current flow. So the ions are moving. The positive ions will move towards this side, the negative ions will move towards this side. Yeah, and just one more thing, it's better if you are familiar with these Roman numerals, then it's easier for you all to figure out the charge and all that. Here I have the Roman numerals 1, 2, 3, 4, 5, and this is 6. See, the I goes to the other side, you can think, then it increases like this and all the way to 10. So these are available also online, you can have a look at them. Alright, then one more thing, I think I didn't write what the N is here, so let's write that right now. N is the number of charge carriers per cubic meter. So in the case of a wire, that is the electrons in 1 cubic meter. So this is the number of charge carriers per cubic meter. Now in this case, if it's a wire, then this will be number of conduction electrons per cubic meter. Number of, because this is what we apply for a wire, okay, maybe I can write it on the side. Number of conduction or free electrons per cubic meter, per meter cube, we can say. So this basically, you can say, okay, this is for a wire, okay, this equation for wire, and this one is the general equation. You can apply it for anything depending on the situation. You can use whatever is Q, whatever is whatever is N, depending on the situation. And it is also given in the last page of this subchapter. Okay, we'll go through this and finish it off. Then resistivity. Table A in section 3.1.4 showed the resistivities of various materials. In the previous chapter, if I scroll up there quickly, you can see the resistivities of different materials. Okay, see here. Similarly, N is also different for different materials. So we will see that N is the number density or number of charge carriers per cubic meter. Okay, I will write it in short also. Area of number of charge carriers per cubic meter, that is the number density. Number density. Number density. Because it is number of something, charge carriers per cubic meter. So per cubic meter, that's where the word density comes in. Number density. Okay. Good conductors, semiconductors and insulators, which are discussed in detail in section 3.1.6, which is the next section. It also showed how the resistivity varies with temperature for metals and semiconductors. Remember, when you heat a semiconductor, it releases more free electrons. The resistivity of semiconductors was seen to fall as the temperature rises, because it releases more free electrons, so the resistivity decreases. Table A below shows how the density of conduction electrons N in the transport equation, table A shows how the density of conduction electrons N in the transport equation explains why the resistivity of metals is so much lower than for semiconductors. Okay, the negative temperature coefficients of resistivity for semiconductors show that their resistivity falls as the temperature goes up. The reason for this is that the value of N in the transport equation will be higher at higher temperatures. So the more free electrons are released. In a semiconductor, when you heat it, it gives more electrons. So that means the N, the number of charge carriers or the conduction electrons per cubic meter will increase for a semiconductor. That's what this sentence means. The reason, see why the resistivity falls as the temperature goes up for a semiconductor? The reason for this is that the value of N in the transport equation will be higher at higher temperature. See section 3.1.6. So in the next section you can see the valency band, the conduction band, and how the electrons are going from the valency band to the conduction band in semiconductors when they are heated. So the fact which makes them better conductors when you heat them. So the fact that the resistivity goes down is actually just a consequence of the fact that these materials like silicon conduct better at higher temperatures, and you can see that here. Now the number of charge carriers per cubic meter, if you look at silicon and germanium, which are semiconductors, the value you can see here 10 to the power 15 to 10 to the power 17, it increased. Here also 10 to the power 19 becomes 10 to the power 20. So both of these increased with increasing temperature. But here you can see this, it became less for copper and aluminum, which are metals, little bit less, right? A slight decrease in N for metals at higher temperatures is due to that thermal expansion. So the volume of a metal increases. So you have the same number, we can say number of conduction electrons, but in a greater volume. So this is number density. Now when the volume increases, the density decreases. Yeah, rather than any change in the number of available conduction electrons. So we can say the conduction electrons remain the same, but when you heat a metal, it expands. So volume increases, N remains the same. Number of charge carriers, number of conduction electrons remain the same, but you have the same number of conduction electrons in a larger volume. So that means the number density, which is the number of conduction electrons per cubic meter, decreases, which means N decreases. Rather than any change in the number of available conduction electrons, it is not nearly as significant as the increase in collisions between metal atoms and conduction electrons caused by increased thermal vibrations. So this is only a small increase, you can see here. So it is not nearly as significant as the increase in collisions between metal atoms and conduction electrons caused by increased thermal vibrations. Okay, so that's the end of that chapter. Make sure you answer all these questions and check the answers in the answer script. And here is the definition. The slow overall movement of charges in a current is called the drift velocity, and here the transport equation. I equals nAvq. I is the current, N is the charge carriers per cubic meter. In a wire, it is the conduction electrons or the free electrons, also called the delocalized electrons, in a cubic meter. And Q is the charge on a charge carrier. A is the cross-sectional area of the conductor, and V is the drift velocity. And remember that drift velocity is somewhere in the order of a few millimeters per second. Okay, of that conductor, drift velocity of the conductor. So next lesson will be semiconductors, and yeah, so this is what we saw. You can see I have shown everything here as well. The quantities in the transport equation, this is very important. Alright then, that's the end of that lesson. So next we will see semiconductors.